So we want to be able to do a quick sine curve always, right? So from -1 to 1 in range, and then my quarter steps, right? And then I know my sine curve starts at 0 to 1 to 0 to -1 back to 0. And there's my sine curve. Of course, I can continue that, right? It goes on forever. But I'm interested in a secant line, right? I'm interested in some point here and some point here, and then the line that connects the two, right? So I am going to ask you to give me a secant, a graph of a secant line on a sine curve or a cosine curve, and calculate the equation of that line. So what do we know about for the sine curve? If f of x is sine of x, right? What do we know about the slope of the secant? How do we calculate that? Anybody?
Is it x plus h
Nice.
minus f of x?
Nice. And we had figured that out to be sine of x plus h, right? Minus sine of x all over h. And so what we're really and what's the equation of a line?
Y minus y1
Nice.
equals m times x minus x1.
Beautiful. And so if we can adjust this a little bit, right? So for example, we're going to put in for this point a comma f of a, and for this point a plus h comma f of a plus h, right? Where h is the distance between the two x values. So for us, right, if we're using this particular slope, and so m subsecant is sine of a plus h minus sine of a all over h. And you're saying, well, why are you bother changing the x to a? Because a is specific, x is every point, right? And you'll see what I do. And so I'm going to use y minus f of a equals that secant slope times x minus a. So that's what I'm going to use on Desmos, right? If I get specific, if I give you the exact value of a, of course you can plug the value of a in. If I give you the exact value of h, you can plug that in, right? So, but I'm going to Desmos here, and now I'm going to build all of this. Nice, so let me use sine of x. That's what I used last time. And let me actually call it f of x. Desmos will get a little confused at first and think that you're multiplying f times x, but you're not, right? It's function notation. Just don't call f a slider. And I want to pick a point a comma f of a. Last time I built this, I built everything with sine of x, right? So now here's my slider a. I could slide using the slider, or I could pick the point on the actual curve and slide that. So that's my first point on my secant line. My second point is a plus h comma, f of a plus h. Again, last time I did this, I used sine for my function. Now I'm using f. So there's my second point. If I drag my second point, you see my value of h changes. If I drag the first point, that second point drags along with a distance of h between them, right? And now I want to connect those two with the secant line, right? Is everybody okay here? Is anybody okay here? Thank you. Thank you. Brian, Jamal, Cindy, Elise, Yvonne, nice. Manish, nice. Oscar, Elmer, Thuria. 12 students out of 18. 6 students missing. I don't get it. Okay, let me put in that equation of the line. So y minus f of a equals my secant formula. Now I want to keep it as f. I don't want to change my function to sine. I want to keep it as a function of x, or a function of a and a plus h, right? So I need f of a plus h minus f of a, all divided by h. That's my slope, all times x minus a. And now I have my secant line. So if I move one point, right, or if I move the original point, there's my secant line. There's my secant line, dynamic, really, meaning I can move the 2 points, or I can, what I really want is to let h go to 0, right? So if I set my first point at 0, 0, and I let h go to 0, right, I can see what's happening to my secant line as it becomes a tangent line. Secant line touches 2 points of the curve, tangent line touches 1. And the beauty is, how the hell can you have a line with only 1 point? That's what I need calculus for. So there's my secant. Now, this is a beautiful thing in that I can now just change my function. I can just change my function to cos of x, and I get a secant line on the cosine curve, right? So there's a secant line on the cosine curve. And of course, I would want you to calculate your secant slope using the points and using the difference quotient, right? What is the difference quotient for the cosine curve? Well, let's see. My difference quotient, or my slope of my secant, is going to give me cos of x plus h minus cos of x all over h. And if I actually wanted the cosine curve at 0, right? So I actually wanted the cosine curve at 0 and then some other point like that, right? I could look at my m sub sec of 0 comma h as what? Cos of 0 plus h minus cos of 0 all over h. And then what happens there? What simplifies? What simplifies?
I have a question.
Sure, Cindy.
So, negative cos 0 and cos 0 plus h. They don't cancel because of the h, right?
Correct, correct.
Okay, I just wanted
So, but the first one does just become cos of h, right? And what is cos
Yeah.
of, what's cos of 0? You can see on my,
0.
it's 1, right? You can see on my black curve at 0, I get a height of 1.
Oh, okay.
Right, remember, and cosine is width. So if I start out at a 0 degree angle, what's the width of my triangle? Even though it's not a triangle, it's 1. It's the radius, right? So this is a pretty important function for calculus. And if you can take a look at my Desmos here, where's my Desmos? What is going to happen as h goes to 0? Right? What is happening as h goes to 0? Where's my secant line? What slope is it going to?
Is it the tan?
Now, what slope do you see it going to? Right at the top of the hill, what's the slope of my secant line going to be? I can't get there, by the way. I can't let h go to 0. It would give me 0 over 0, right? But what slope do you see? What calculation? Let me see if I can go to 0. There you go, 0.01, 0.001, 0.00. What slope do you see I'm getting to? Oh.
Is it a hole?
Nope. Look at that purple line. What slope is that?
Is that asymptote?
It is. It's a horizontal one. Not really, but what's the slope of it?
0.
Exactly. So if you remember from Monday, we had the m sub sec of 0 comma h of sine. We had sine of h over h, and that went to 1. That slope went to 1. And if we have the secant slope of 0 comma h now of cosine, we have cos of h minus 1 over h. What is cos of 0, by the way?
1.
Good. So upstairs I get a 1 minus 1. Downstairs, that's 0. And downstairs I get a 0, so I get a 0 over 0. And that one goes to 0. So sometimes when I get a 0 over 0, I get a 1. Other times when I get a 0 over 0, I get a 0. This is what's called an indeterminate form. How we doing? You can't just watch me do this stuff. You can't just watch me parallel park and be able to parallel park as good as I do, as well as I do. So you have to practice. So I'm asking you to try and build one of these dynamic secant lines, right? Build one. It will open up some real insights for you. Okay, I think we're ready to do the new stuff. Unless anyone else has a question for me. Nice. So we're talking about 6.6 graphing sine and cosine with a phase shift. And our whole picture is y equals plus or minus a times sine of b times the quantity of x plus c, all plus d. And we talked about what each of these things are. I put them in alphabetical order because I want you working on them in alphabetical order. The book does it differently, a little bit more confusing if you ask me, but this is my reflection. A is the amplitude, and the easier way to think of that is it's the radius of the circle. B is called the frequency. I like thinking of that as the speed of a point moving around the circle. C is my phase shift. I think it's easy to think of that as the horizontal shift, right? And the start. I want to think of it as the start. That'll make a little bit more sense later. And finally, D is called the midline, or the vertical shift. So if we take a look at this piece that I created on a program called Geometry Sketchpad, and I would say computer scientists, maybe math majors, is Ben here today? No. You would try and want to build this on either GeoGebra or Desmos. So, but I can see here, I'm going to return back to my sine function. You can see my original purple function is the sine curve, and it's going on forever and ever. But I'm focusing in on this rectangle. Like when I did the transformations of other functions, I had that little 1x1 box that I was manipulating. And now I'm going to be manipulating this triangle, rectangle. And once I get the rectangle drawn, of course I know the pattern for sine, right? Or I know the pattern for cosine, right? And so I can put that into the box. So you can see here, I've got an amplitude up one and down one. So the height of my box is double the amplitude. I've got a width of 2 pi, that's the period, and you can see my quarter steps, right? And so just if I adjust A, the value of A, you can see I'm just going to increase the radius or the height of the box, right? So now I'm going up to 2, down to -2, but still the same pattern for the sine function. If I shift C, it's pretty easy to see my shift of C is going to move the whole box. If I C is negative, my box is moving right? If C is positive, the box is moving left, right? So C is actually the opposite of C is always going to tell me the starting point, right? Always telling me the starting point. So I want to figure out where my box is going to start, right? And that's C. And remember, I gave a shortcut to C. I called it the start. D is pretty easy in respect that if I move D down, the midline, that center line, what used to be the x-axis moves down, right? Or if I move it up, it moves up in the air. Typically, I don't bother with D. It's enough to do everything else that I won't bother with trying to figure out or putting in a value of D. So meaning my midline, the middle of that rectangle will always be the x-axis, right? If I set D at 1, then, of course, right, the middle of that rectangle is now at a height of 1, right? So the tricky part is when I change B, right? The tricky part is when I change B. So I'm going to return everything back to my original sine function, and now look at B. What happens when I make B larger, right? When I make B larger, so for example, right now I have B at around 2. Look at what happened to the period. How wide is that rectangle now?
Pi.
Pi. So, and notice that B value is in the interior of the function. So even though it says multiply by 2, it's actually dividing by 2. It's taking the period and cutting it in half, right? So we have to have this thought that our period is always going to be 2 pi over B. So a period is always going to be 2 pi over B. Look at what happened to the quarter steps. Are they the same size? If I remove B back to 1, whoops, wrong tool. If I remove B back to 1, you can see it's 90 degrees. It's pi over 2 for all of my quarter steps, right? But if I set B at 2, right, now all of a sudden it's pi over 4. So I have to, after I get my period, I divide the period by 4, I get my quarter steps. So quarter steps, oops, is the period over 4. Now it gets even worse if I have a starting point, if I start somewhere else, and that's what we're going to work on today. I'm going to start somewhere off and change the frequency, that B value, and now I have to figure out the start, I have to figure out the quarter steps, in fact all 5 steps from start to the last quarter step. Right? So that's what we're working on today. Everybody with me so far? Nice. So let's jump right into one that has just a phase shift. Okay, I think the amplitude is easy. I think the start is easy. I think the midline is easy. It's when I have a phase shift and a frequency change that it gets pretty tough. So let's just deal with the phase shift first. So something like y equals sine of x minus pi over 4, right? So every time I do this, I'm going to say, what is A? Well, A is 1, right? The amplitude is 1. It's a radius of 1 here. What's the value of B? Well, B is 1. There's no, right? The coefficient in front of x is 1. And if it's not, I want to factor it out, right? I always want that y equals sine of b times x plus c. I always want that b value factored out, okay? At least that's the way I'm teaching it. The book is doing it differently, okay? What is c? Where do I start?
Negative pi over 4.
Positive pi over 4, because I'm always trying, remember x's behave inversely, so I see the negative, but I really want the positive.
Right.
Yeah, and my real thought is, what x value makes that green part 0? What x value gets me back to the garden, back to the mother function, back to the origin, right? And so it's obviously pi, a positive pi over 4. D is, well, I need the period. Once I get B, I need the period, sorry. So the period is 2 pi over 1, so it's still 2 pi. Still just like the mother function. I need a quarter step, and I do this every time. I take the period over 4, so I get a quarter step of pi over 2. I take my start, pi over 4, and I take my first step. I do this every time. My first step is pi over 4 plus the quarter step. So what do I get there? For the first step, what do I get? Three pi over 4. Very good, class. 3 pi over 4. So now I can see that I've got my... Yes?
I have a quick question.
Sure.
So for the period, how did you get 2 pi over 1?
It's always 2 pi over b.
2 pi over b.
Over b, yep. I had written that on that sketch pad one, right? Period is 2 pi over b every time. So now I can see my start and steps are pi over 4, comma 3 pi over 4 what am I adding? I know this is arithmetic. I know the sequence is arithmetic because I know I'm adding the same quarter step every time. So what comes next? 1 pi over 4, 3 pi over 4, what comes next? Good, 5 pi over 4, what comes next?
7.
Yep, 7 pi over 4. And finally, my last quarter step will get me to 9 pi over 4. I'm going to do the same process every time. Once I get to start and the first step, I can use my knowledge of arithmetic sequences to know what the whole sequence is. Right? D, of course, is 0, so we're not going to change our midline. And now we have everything we need to graph this function. I'm dealing with pi over 4s. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm using the bigger dash marks as the ones I know I need. Right? I've got a pi over 4, a 3 pi over 4, 5 pi over 4, 7 pi over 4, 9 pi over 4. I know my amplitude is 1, so I'm going down to -1 and up to 1. And my rectangle is set. Here's my rectangle, and I can see the quarter steps. And then I know the pattern for my sine curve. There it is. What do you think? It's okay. You must practice. You must have step by step written down. You must be practicing, right? Let's do another one. Can I move on and do another one? Anybody need a moment? Let's do y equals 3 times the sine of 2 times x minus pi over 3 plus 0, so no midline. Right? Good. I know what the original function looks like. 1, 2, 3, 4 quarter steps, max height of 1, min height of -1. I can see that rectangle, right, with my quarter steps. I certainly can see the start, right? I'm just doing the original sine function, the original mother, right? I see that my amplitude is 3, right? So that means I want to rebuild my rectangle to a height of 3. Or actually, the rectangle is all going to be a height of 6, right? The whole diameter, up, the radius above and the radius below. My picture is going to change, right? But my quarter steps are going to stay the same, but everything's stretched out high. So here to here to here to here to here. And there's y equals 3 sine x. How we doing? Jamal, thanks. Cindy, great. Wilder, nice. Elise, thank you. Yvonne, nice. Oscar's, oh, Oscar's awake. Brian's there too, nice. Elmer's there. Okay, let's put in a frequency change, right? So let's go to y equals 3 times the sine of 2x. So now I'm looking at b as 2. Is everybody with me?
Yeah.
So that means the period is 2 pi over 2, which is just pi. So remember, when I'm multiplying on the inside, I'm actually scrunching, right? I'm compressing that width of that rectangle, right? So I know my period, I know my quarter step, is pi over 4. I always take the period and divide by 4, right? Quarters, 4 quarters. So my quarter step is pi over 4. Where do I start? I'm still starting at 0, right? Starting at 0, right? What makes this 0? What x makes that inside 0? 0. And so obviously I don't really have to think about this process too much. 0 pi over 4 to 1 pi over 4 to 2 pi over 4, right? 0 pi over 4 to 1 pi over 4 to 2 pi over 4, right? Does that make sense? 3 pi over 4, and finally end at 4 pi over 4. So this is my start and steps, right? But that was so easy I didn't have to really do anything. Now let's look at the picture. Let's look at all 3 that I got, right? So I had 1, 2, 3, 4, all the way to 2 pi. I had a radius of 1, and then a new radius of 3. My original rectangle for sine was here. Is everybody understanding that? And I know where those points meet. I know the pattern for sine functions. So far? Then we changed our amplitude, right? And we said, well, let's go up to a height of 3 and down to a height of -3. And my rectangle is just a little bit different, a little stretched out this direction because I'm multiplying on the outside by 3. And I'm still seeing that same pattern, only looking at that blue rectangle now, though, not the green one. Now, when I finally get to my y equals 3 sine of 2x, I know the period changed from 2 pi to pi. So I have to, my rectangle is half as wide now. Here's my new rectangle, right? And I need quarter steps, right? So I need everything cut into 4 this way. And I know my pattern for sine is 0 to the max, back to 0 to the min, back to 0. And there's my, so now you can see what used to take me all the way to 2 pi, I finished in pi. And I'm saying the frequency is twice as fast. Meaning if I kept going with another version of sine, I would have it repeated twice in what used to happen once. Twice as fast. Right? The sine wave repeated twice instead of once. That's frequency, that's speed. I wouldn't go more than this. I did mother, daughter, granddaughter. I wouldn't go great-granddaughter. In fact, we can go great-great-granddaughter if we have a midline as well. So I just want to go and do this whole final one now. Y equals 3 sine of 2 times quantity of x minus pi over 3. We had already figured out that the period was what, 2 pi over 2 was pi, right? And that our quarter step is pi over 4. I always just take the period divided by 4. And what's my start now? What's that value of c?
Pi over 3.
Nice, pi over 3. So I want to think of the first step. I do this every single time. It's pi over 3 plus a quarter step, so plus pi over 4, right? And of course I get 7 pi over 12 there, right? Does everyone agree with me if I do my LCDs? Seven pi over 12, yes? Nice. I want the start to look like it's coming from the same family, so I'm going to change my start to a pi over 12. And so I get, what, 4 pi over 12 for my start. And because I can notice that I'm adding what? From my start to my first step, I'm adding 3 pi, right? I'm actually adding 3 pi over 12. I'm going to keep adding 3 pi over 12 every time I move forward, right? So my start and steps are 4 pi over 12, to 7 pi over 12, to 10 pi over 12, to 13 pi over 12, to 16 pi over 12. So I'm now ready for my rectangle. I know I need a height of 3. And I know I'm starting at a pi over 12, so let me get there. 1, 2, 3, 4 pi over 12. That's where I'm starting. 5, 6, 7 pi over 12. 8, 9, 10 pi over 12. 11, 12, 13 pi over 12. 14, 15, 16 pi over 12. That's where I'm ending my rectangle. So I can see my rectangle from here to here with a height of 6 and my quarter steps. And then I know, of course, the pattern for sine. 0 to max, to 0 to min, to 0. And there's my sine. There's my final answer. Ouch. Right? Am I right? Headache? Yeah.
Yeah.
Now on my sketch, I definitely can see that, right? I had what A is 3. Let me close this and open again. I can't use the pen on here, it doesn't like it. File, open. So I had an A of 3. Close enough. I had a B of 2. I had a C of pi over 3. What's pi over 3? About 1.05. And there it is, right? There's my graph. So, oh, why is D? I should have D as 0. Sorry. Right. So, of course, you can graph this in your calculator, right? Just as a quick double check. If I were to do this on my calculator, I'm going y equals 3 times the sine of 2 times parenthesis x minus pi over 3, close, close. I like to zoom trig. For my trigs, I like to zoom trig, zoom 7. I'm really looking for that thing, that version of the sine that's closest to the origin, right? So if you can look at closely, you can see my mouse moving. There's the beginning of the sine function, right? And then there's the end of it. And that's the piece I'm looking for in that rectangle. So, but what's kind of nice, if I change my table set, I change my window to start at what, pi over 3, right? Right, we started at pi over 3. and my maximum was 16 pi over 12, right? And my scaling, I really want to be moving by those pi over 12s, right? And then you'll see the one version of your curve, right? Every 3 tick marks is a quarter step, right? Because we're adding 3 pi over 12 every time. How are we doing? Let's pick one from here and then quit for today. Pick one for me, somebody.
Sorry, I
Can
was
you do
excited.
one with a D?
Yeah, so 9, I guess. 9 or 10. Yeah, there's a couple tricky ones there, but that's fine. I guess 9. 9's fine, right? So y equals 4 sine of... Oh, should I do a cosine one? Should I do 10? Let me do 10. These are a little bit more difficult than what I'm going to give you. I'm going to give you one just like I just did. These get a little weird. Because they want to see if you can do it. They want to see if you really understand what the heck's going on. So I've got 6.6, number 10 from the book, right? And I want to graph y equals 2 times the cosine of 2 pi x plus 4, all minus 5. So my midline is minus 5. Oh, I'm sorry, plus 4, right? So I'm going to move the whole rectangle up 4. Nice. First thing I want to really do is factor out that leading coefficient of x. So 2 times the cosine of 2 pi times x plus 4 over 2 pi. Make sure you're with me there. I'm not going to put a pi in your problem, okay? So we can simplify that. Y equals 2 times the cos of 2 pi times x plus 2 over pi. Of course, they just make their numbers pretty nasty. I'm not going to do that to you. What's the amplitude? Good, class 2. What is the b value, the frequency?
2 over pi.
Just 2 pi. Just 2, right? Whatever that coefficient of x was. And so now I should be able to get the period of 2 pi over 2 pi, which is 1. So it's going to repeat after x is 1. Whether that's radians or not, it doesn't matter, okay? But I know my scaling on my x-axis is going to be 1. What's a quarter step?
1/4.
Yep, it's always that easy. Take the period and divide by 4. What's my starting point? Very good, class. -2 over pi. So this is where the numbers start to get hideous. 2 over pi is about what? What decimal? 0.6 something? 2 divided by pi. It's 0.64, maybe, right? So pretty nasty. But let's look at our first step. I'm going to give you one that's nice. Our first step is -2 over pi plus 1/4. I have to add the quarter step, right? So it looks like I get, I'm going to get a denominator of 4 pi, right? So I need a 4 over 4 here and a pi over pi here. So it looks like I get pi minus 8 over 4 pi. Now I want my start to look similar, right? And that's what, minus 8 over 4 pi. So it looks, so what did I add from the start to the first step? What did I add? What did I add? Just looking at the numerators to make it simple for you. I started at minus 8 and then I went to pi minus 8. What did I add? I added pi. So I got a minus 8 over 4 pi, pi minus 8 over 4 pi, 2 pi minus 8 over 4 pi, 3 pi minus 8 over 4 pi, 4 pi minus 8 over 4 pi. Hideous. Hideous, hideous, hideous. If you look at this end minus the beginning, the end minus the beginning, end minus the start, you see I have 4 pi minus 8 over 4 pi minus a negative 8 over 4 pi, which of course gives me 4 pi over 4 pi, which is 1. Right? I knew the period was 1. So from the end to the beginning should give me the period. The rectangle's hideous, I'm sorry. It's hard to do this. Again, the one I'm going to give you is it's much nicer. I'm going to start at minus 8 over 4 pi. So I'm kind of just pretending here. So there's my minus 8 over 4 pi. There's my pi minus 8 over 4 pi. There's my 2 pi minus 8 over 4 pi. It'll be much nicer, the one I give you, okay? Now, that gives me my start and end and quarter steps. I also know my amplitude is 2, right? But I'm raising it up, what, 4? So my midline should be at 4. 3, 4. There's my midline. And then 1, 2 up and 1, 2 down. Here are my quarter steps, sorry. And my height is 2. And it's a cosine curve. So 1, 2, 3, 4, 5. There it is. Ugh, horrible. Whose idea was it to give you those problems in the book? I think I like 1 to 8 better. It won't have any of those weird things happening in it. Number 9 gets weird, 10 gets weird, 11 gets weird, 12 is weird, 13 is fine. You can do 13 and you can do 14. So let's say 3 to 8 and 13 and 14. Don't do any of those weird ones in the middle there.